Okay, so hello and welcome everyone to our sixth session on OpenMP programming. So in the previous session, we saw how to parallelize the trapezoidal proof, right, in multiple ways. Later, we also saw something called as reduction and how to use the reduction clause in OpenMP. And later, towards the end, we saw something called as parallel for directive. And we saw a few examples related to parallel for directive. And then we also saw the limitations related to the parallel for directive. And towards the end, we were at this slide, right? We were talking about all the limitations that we have. And yeah, and later we also were looking towards the end this program, right? Let me share that. So we were looking into this program, right? And yeah, as we discussed that this program in serial will return for, I mean, it will print 45, right? That is what we were looking, right? So just quickly checking that. Uh, so this program will print 45 and we saw that thing, right? Now the point here is that we want to understand what will be the output of this program in parallel when we run it in parallel using hash pragma or mp parallel for and then adding reduction for this sum variable and for this plus operator. So please think about it. What will be the output of this program? So using this, I want to derive a particular point and hence I'm asking. So please try and find the output for this function, just do work. We'll do work one. We'll discuss about do work two as well. But first of all, let us try about this do work one. What will be the output? After writing this hash pragma mp parallel for and reduction. Please try on your own and yeah, do let me know what can be the output. I'll wait for a few seconds here for you people to try and then we'll discuss. Okay, no response. Anyone who would like to share the output or anything weird about this program? Anyone? Okay, okay, then I'll go ahead. So if you see this program, and if I try running this program, right, let us do that. Let me share a new screen. So if I try running this program using this OpenMP flag, right, it compiled. Now we are running it. So did you observe one thing? It is giving 47 instead of 45. So if you remember, our serial code was giving 45. So here we are calling do work one and do work two. So in do work two, okay, let me go back. Yeah, so here we are calling two functions, do work one and do work, and this is the output for do work one, first one, and it is giving 47 instead of 45. So if you remember for the serial code, if I, okay, let's just quickly run it. If I remove this app OpenMP flag and run it serially, then if you remember, it was giving 45, right? But when I place this app OpenMP flag and if I run it, it is giving 47. So what is wrong that is going on with this code? So let us see that. So let me share this code again. So if you see here in this code, what we are doing with this code, we are, I mean, we are running this for loop in parallel. So this is a work sharing construct. Hash pragma MP4 is work sharing construct. So iterations will be divided among threads, and uh, during each iteration, what we are doing is we are incrementing a of I to a of I plus 1, and then we are summing it up, right? What we are doing? What we are adding in sum? A of I plus 1. So let us see what will happen in this case. Let me share my whiteboard now. So yeah, quickly, let me pull this out. So what will happen here in this case is that we have this array of 10 elements, right? So we have this array of 10 elements going from 0 to 9. So let me number it 0, 1, 2, 3, 4, 5, 6, 7, 9. So what is happening here is that this thing, we are doing this thing, right? A of I equals to A of I plus 1. And then sum equals sum plus A of I plus 1. Now, what can go wrong here? So let's say the iterations are divided among threads. So let's say 0 and 1 elements, or let's say, yeah, these two elements are being operated by, by thread 1 or thread 0. And let's say these two are being done by thread 1 and so on. Now, what can go wrong here is that in the serial code, uh, this iterations will execute one after the another. So here in the serial code, this increment of a of 2, I mean this element will only happen after the previous iteration where this part is updated, right, using uh, by reading a of I plus 1 will happen only after this is executed. But when threads are executed in parallel, T1 can execute before T0 also, right? So what might end up happening here is that A of sorry, this statement, right? Thread 0, thread 1 might execute this statement before thread 0 does this. So okay, well, let me put it in different color here. So before T0 does this thing, T1 might end up doing this one. So what can happen here is that this will be incremented first. So initially it would have been 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? Because it's summing values from 1 to 9. But since this is executed first, what can happen is that this will be incremented first. So this will become 3 first. And then T0 is reading this value, which is A of 2. For T0, it is doing A of I plus 1. So A of I plus 1 is nothing but A of 1 plus 1, which is A of 2, right? So it is reading this value 3 instead of 2 because T1 has executed the statement first, right? So here, what is happening is that it will add 3 to the sum instead of 2. And this is happening because ordering is incorrect here. And in serial, we are sure that this statement for next iteration will be executed only after this statement is done for the previous iteration. And this thing is called loop carried dependency. So formally speaking, when the element of the array, when any element of the array, in this case, which is 3, or let us say this one, is being read by some iteration and is being written by some another iteration. So in this case, 3 is being, this A of 2 is being read and also written by some another thread, right? Because thread 2, let us say thread 2 will, not thread 2, but let us say that this element is being operated by some another thread. Then it will try reading this. T1 will try reading this from this element, and at the same time, it will write into this element, right? So essentially, the point is that if I specify it more clearly, let me draw it again so that we can be more clear. So if you see at any point in time, let us pick 0, 1, 2. This element a of 1, right? Or let us say this a of 2, it would be easier with a of 2. So at any point, okay, let me switch this. So I hope you are able to see the new board here, new whiteboard here. So at any element, at any point in time, this a of 2 is being read by the some thread, I mean, in some iteration, and is being written by another thread in different iteration. So a of 2 is being written here by, if you see here, a of 2 is being written using this statement, right? If you go, a of 2 will be written by this statement by the thread, some thread, right? So a of 2 equals to a of 2 plus 1. So there is some writing operation that is happening. And at the same time, some reading operation is being also happening on this same element of the array, right? Which is sum equals to sum plus a of 2. Now, this can be, I mean, this can be done by two different threads in two different iterations, right? So as we saw earlier, this can be executed by thread 0, and this one can be executed by thread 1. So in general, this thing is called as loop carry dependency. So if there are two threads, I mean, there are two, if there is this element of the array which is being read and written in the different iterations of the loop, then there is the chance that we might encounter this scenario, which is loop carry dependency. And when this happens, will encounter, I mean, will have this kind of result, right? So if you see here, as we saw here, that the output might get incorrect. So this is what is loop carry dependency. So let us move back to the slides. I hope that I made this point clear. If there is any confusion, then do let me know. So going back to the slides, so yeah, this is what is the loop carry dependency, and this generally happens when the same element of the array, in our case, it was a of 2. And when the same element of the array is being written in one loop iteration and is being read in another loop iteration, or it is written in two different loop iterations. This can also happen. So if that element is being written in two different, is being written by two different iterations, then also we can have this loop carry dependency. So I hope the example that I gave was clear. So in that example, that a of 2 was being read in one iteration and was being written in another iteration, and that two different iteration can uh, might, I mean, that two different iteration might be picked up by two different threads, and in that case, there might be some issues. There might be the this loop carry dependency that can happen. So yeah, so this is clear now. Yeah, so in this case, what is happening is that element in one iteration depends on the other iterations of the loop, and this is leading to the loop carry dependency. And the most problematic part is that, as you saw, right, the OpenMP won't warn you for this. It will give the wrong result. It won't warn you that there are loop carry dependencies in your program. Please fix it. It won't say that. It will just produce the wrong result. So the only way to avoid is that you need to look the uh, iterations of your loop, and you need to see whether there is any variable which is being read in some iteration and written in some different iteration. If that is the case, then there is loop carry dependency, or it is being written in two different iterations. If that is the case, then there is loop carry dependency. And you should avoid parallelizing such loop by placing hash pragma OMP parallel for. So I hope that this point is clear. If there are any questions around this one, then do let me know. Are there any questions? Okay, if there are no questions, then I'll ask one question here. Let us switch back to our code. Are there any loop carry dependencies for work 2? To work 2? Are there any loop carry dependencies in this code? I mean, for this function, do work 2?
Yes, sir, there is.
How?
we are updating B of AI in this, right? So AI might be something else, like we're assigning it over there in the first loop. So the same element is getting updated, but in a later iteration, it will get read by and be supplied into sum is equal to sum plus one, sum plus bi. Sorry.
Yes. So in general, your answer is correct. And but if you observe here, we are updating. Sorry, we are initializing a of I to I. So there might not be the issue here. So it can potentially lead to the loop carry dependencies. But if you observe here, there won't be any loop carry dependencies here. The way we are initializing this a of I. So let us go back to our whiteboard again to explain it better. So here, in this case, there won't be loop carry dependencies because what each thread is doing is that, let me change this. It is doing B of A of I, and I think it is initializing it to something. Let me quickly check that. Yeah, it is initializing it to I. B of A of I equals to I, and then what it is doing is I think sum it is updating sum. Yeah, sum equals to sum plus p of I, right? It is doing this thing. Now, this won't lead to loop carry dependencies, what I'm saying, because a of I is initialized to I. So essentially what we are doing in this statement is that we are doing p of 0 equals to 0, p of 1 equals to 1, and so on, right? So we are doing this, and for each thread, each iteration might be assigned to one particular thread only, right? That we agree, right? That for any one particular iteration, it will be assigned to a single thread only. So this statement, what it will do is it for each thread, it will initialize it to 0, 1, 0, 1, 2, 3, and so on. And then also we are accessing B of I only. So when each thread access B of I, let us say that two different threads are assigned to two different elements. And when they try accessing B of I, they are not accessing some another element. I mean, this won't lead to the case where same element is being read or written or being written by two different threads in two different iterations, right? Because let us say that thread 0 was working on this and thread 1 was working on this one. In this case also, this initialization will happen independently, right? They'll initialize a b of 0 as 0 and b of 1 as 1, right? And that won't interfere, right? There won't be any overwriting or something like that. This will happen correctly. And then they are reading it also correctly. I mean, they are reading it independently and not the same element they are reading here. They are reading two different elements, which is p of 0 and p of 1. So this also won't lead to any issues, right? They are reading and writing the different elements. So the important point to note here is that there is no loop carry dependency here because reading and writing is happening on different elements. And hence there is no loop carry dependency here. So I hope you got the point. In previous example, that is in do work 1, there was this thing, right? Reading and writing was being done on the same array element. So for a of 2, reading was being done as well as writing was being done. So reading was being done using this a of I equals to a of I plus 1, and writing was being done by using a of I plus 1, which was the next statement, right? So two different threads can access this a of 2 at the same time in two different iterations. So here reading and writing is being done, I mean, on the same element, which is not the case for this one. Here reading and writing are not happening on same, they are happening on different elements by all the threads. So any questions? Why we are saying that do work 1 is facing loop carry dependency and why do work 2 is not? Then do let me know. Okay. Yeah. So based on what we learned, this is here loop carried dependencies are there, and for this one there are loop carried dependencies, and for this one there are no loop carried dependencies, right? So okay, let us try to run this also. So this one is already running in parallel, and I think we already saw that, right? That even after running in parallel, let me switch back to the console. Yeah, so even after running it in parallel, this uh, walk to, which is the second output, is giving 45. You can try running it n number of times. It will always give 45 because there is a potential chance of loop carry dependencies, but there are no loop carry dependencies because the way we are accessing the array elements. But yeah, for walk one, there is a loop carry dependency. So, and hence it is giving this ambiguous result, which is other than 45. Okay, I am hoping that we are clear with what is loop carry dependencies and the example that we saw. Then, okay, let us switch back to the slides and look into the next thing that we want to see. So next thing that we want to see is atomics. So atomics are nothing but it provides us the way to mutually, to access the particular statement in a mutually exclusive manner, as we saw in the case of critical. So uh, the main difference here is that, okay, let me share the whiteboard. So if you see, we already have a critical directive, right? And why we need this atomic directive? So let us say this also. So if you remember, we have this thing, right? Pull this out. Yeah, we have this thing, right? Critical, right? So in critical, what we are doing is hash pragma OMP critical. And what was happening was that the structured block of code, right? Structured block of code that was following after this hash pragma OMP critical was executed in mutually exclusive manner by all the threads. But in this case of hash pragma OMP atomic, so this is the syntax of hash pragma OMP atomic. So this is the way we define it. The single statement, right? Single statement that follows this hash pragma OMP atomic will be executed in mutually exclusive manner. And it's not just about this single statement, it has further more restrictions on it. So this statement can be only of type variable equals to variable, then operator, and then some expression, or it can be some function, variable equals to some function. And again, there should be first parameter of this function should be this variable, and then you can have some expression here again. So this is what this statement should look like. So one thing is there should be only one single statement after this hash pragma OMP atomic, on which it will ensure the mutually exclusive access, and this statement should also be in this form. And another restriction is that this operation should be only plus, minus, multiplication, division, and some bitwise operator like and, or, and so on. So only arithmetic and bitwise operators are allowed. Also, there is one more restriction, which is this expression should not contain this variable var. So these are all the restrictions that we have on this hash pragma OMP atomic. So if you see, this hash pragma OMP atomic is very restrictive, but then what is the advantage over this hash pragma OMP critical? If there are so many restrictions, the key advantage is that the key advantage here is that this one will be this one is faster than hash pragma OMP critical. And that is because if you see, when you have this statement like this or this, what essentially is happening is that this expression expr can be executed in parallel. Only thing that we need to ensure here is that loading and storing of this variable var, which is load and store on this variable var should happen in atomic manner, right? So here there is loading part, and here when we are reading this var here on the right hand side of the equation, there is loading part. And here on the left hand side, when we compute this entire equation and when we are trying to write it, there is this storing part happening, right? So we only need to ensure that load and store on this variable var is happening in atomic manner. So that's why it is faster, because here in this case of critical, if we remember, we need to, the OpenMP need to ensure that this entire structured block of code is being executed in a mutually exclusive manner, which is which needs more it is more general than this thing, right? Just executing load and store in atomic manner. So that is the reason this hash pragma OMP atomic is much quicker. It's quicker than hash pragma OMP critical. So in general, we should try using hash pragma OMP atomic if possible over hash pragma OMP critical. Not always it will be possible because of all these restrictions, but yeah, you should try using this over critical. So going back to the slides. Okay. Yeah, so as I explained, the mutually exclusive access will be given to the statement which follows this atomic directive. And it only allows one thread to execute a particular statement, as we saw, right? Only one particular statement will be executed in a mutually exclusive manner. So that is what is given in point 2. And we saw the syntax, right? Hash pragma will be atomic. And yeah, these are the two statements that two varieties of statement that can follow this hash pragma will be atomic. One is variable. We saw these two things, right? And yeah, these are the operators that it can take, and expression expr should not have the variable var. So these are all the restrictions. And yeah, as we discussed, right, that only load and store are atomic, and hence it provides more optimized way to get the mutual exclusion over hash pragma and the critical. But this comes along with the restrictions that we have. Any questions up till now?
I have one question.
Yeah.
The previous column LCD that we have discussed, loop.
Yeah.
That will be solved if they are atomic in section.
Sorry, can you repeat? Can we solve it using atom? Is that the question?
To do work one, if we make it as not a parallel, and if we make it as atomic unit, then this LCD problem will be solved, because load and store is going to be atomic operation, right? So there won't be, until a thread does the loading and storing, no other thread can have access to that variable.
Yeah, this is a good question. And I'll ask this question to every one of you. Let us say that, okay, let us say that I remove this reduction, right? And let us say that I place the critical section. So what you were suggesting is that if we do loading and storing in atomic manner, or let us say that even before coming to loading and storing, let us say that we do this, right? This thing, we place this entire thing in critical section, right? So not just loading and storing, this now statement entirely are executing in the critical section. So apart from loading, storing, everything will be done in one at a time, right? By each thread. Will this solve the problem? Is the question, which is a good question. Will it solve the problem? Request everyone to try this out. It is a very important exercise. Can you try? What will be the result? Will it solve the problem? That is, will we get? Okay, sorry, I think I have placed it in our wrong function, but yeah, let us move it here. This is the one that we are looking at. This do work one. Do work one is the one which is having loop carry dependency. So placing it here, will it solve the problem? Will we get the output 45 always, or still we'll get some different output apart from 45?
So we'll be getting a different output, and the reason for that is we cannot control the order of execution of the threads that are launched.
Yes. So the important point here is that loop carried dependencies occurs due to the ordering. I mean, because of the different ordering of the threads. I mean, different ordering in general, the way they're reading and writing on that particular element of the array. The order in which they are reading and writing on that particular element of the array. And even after placing this thing, hash pragma OMP critical, you still can't control the ordering, right? What you are doing is that you are telling that just run this thing in mutually exclusive manner. And that doesn't mean that you are restricting some ordering. You are just telling that one thread should execute it at one time. But which thread will execute it first is not in your head, right? So coming back to our whiteboard thing, so let me put it in a better manner. So even after placing this entire thing in critical section, what can ideally happen is that this thing, right? This ARR of 2, still it can happen that let's say this one was being executed by this way. So okay, so let me do it in this way. So what thread this is being executed by some thread 2, and let's say this is being executed by some thread 3, ARR of 3. So what T2 will do, it will try to do ARR of 2 equals to ARR of 2 plus 1, and then it will do this, right? It will do sum equals to sum plus ARR of 3. And what T3 will do? So T3 will do this thing. ARR of 3 is equals to ARR of 3 plus 1, and sum equals to sum plus ARR of 4. Now, let us say that each thread, right? This is being executed by thread 2, and this is being executed by thread 3. Now, let us say that each thread is executing in mutually exclusive manner, right? It is executing its sets of statements in mutually exclusive manner. Even then, what can happen is that this thing, writing, this part, writing of ARR of 3 equals to ARR of 3 plus 1 can happen first before this reading by thread 2. And if that happens, then you will see that this ARR of 3 has some different value, right? And ideally, it should be 0, 1, 2, 3. It should be read as 3, right? It should be read as 3, but if this increment happens first, then it will be read as 4. And if this is being read as 4, then 1 plus 2 plus, it will not take 3, it will take 4 plus 4 plus 5, sorry, plus 5 plus 6, and so on. So it will output something that is greater than 45, because we are not summing now from 1 to 9. We are summing from some, I mean, we are ideally we want to sum from 1 to 9, but in between some different values can pop up, right? Like 4, because of incorrect reading that can happen here. So I hope you understood this thing, that even after placing the critical, the order in which the threads are executing, that you can't control. And that is the reason you won't be able to use any synchronization like critical or atomics to fix this loop carry dependencies. The only way is to identify it and make sure that if there are loop carry dependencies, you run it in serial. I hope that answers your question.
Yeah, I get it. I have. I also asked the similar question in one of the previous sessions. You have already answered it, but still I wonder. In any way, there must be a way to the control the order of execution of threads. I think so. I don't know.
Yeah. So if there is any, then we can use it. But I think okay, I'm not aware about such way, but yeah, I think I need to look. I think I mentioned the same thing in that lecture also, right? I am not aware about such any construct that we have to order it to control the ordering of the threads.
Maybe based on the thread priorities or something. Sometimes there may be occasion. I'm just speculating. I don't know. Based on the priority of the thread, we may need to control their order of execution. I think so. I'm not sure.
But such priority based addressing, I'm not sure if OpenMP provides, but yeah, we can check. We can check if there is something. If that's the case, then we can solve this loop carry dependencies problem.
Okay, thank you.
Okay.
So I
Anyways,
have one
let
more
us.
question.
Yeah. Yeah.
So this atomic clause basically allows us, it's efficient because it only does the load and store on the variable, right? But
Yes.
this was also the case when we introduced the reduction operator for all those parallel clauses as well, right? Because the reduction operator
Yeah.
makes a private copy in the thread itself, and then it updates the shared variable after that, right? So what's the difference between using an atomic an atomic clause and like using the reduction clause in a parallel or parallel for or any other clause?
So that's a good question. I think both must be similar, but yeah, I need to check that if there is any performance advantage that one gives over other. But yeah, the kind of functioning is similar because yeah, as we discussed, right, that similar kind of things are happening with atomics and reductions. Yeah, reductions and atomics. Yeah, I'll check this one if there is any advantage of using one over other one.
Okay, so thank you.
Yeah, so the next one is barrier. So barrier will provide the explicit synchronization for the team of threads. So let us move back to our slides. Okay, I think one more thing that I wanted to cover before variance. So this Hello World program that we saw, right? We'll quickly touch upon this. So here in this program, right, we saw this in our third session. So in this, we are doing this sum equals to sum plus DI. So instead of using critical here, we can do atomic here. And this will make this code slightly more efficient. So that is one place where we can use atomic, just to briefly touch upon this thing. Now let us quickly move to barriers. Yeah, so barriers provides the explicit synchronization point for our team of threads. And the syntax is highly simple, hash pragma MP barrier. And what will happen is that each thread will wait for all other threads to reach that synchronization point, right? So that is what is hash pragma MP barrier. Now let us do one more example with barrier also so that we can understand it in better manner. So, okay, sorry. Let us move back to our code. Yeah, this one will work. So let us say that we have this, right? If PID equals to 1, let's see something. Let's say we do this and yeah, and then we place this hash pragma 1. Yeah, right. So we are doing this. So normal our hello world program in which we are launching this hello function in parallel using num threads, and then we are doing this calculation entire thing, and then at the end what we are doing is if TID is 0, we are saying hi from thread 0, and inside that we have this barrier hash pragma barrier. What will be the output of this program? A quick question. What will be the output? So I hope you understood the question that I'm trying to ask. That I want the output for this program, and we have just added this simple check here, as well as hash pragma MP barrier. What will it print? And yeah, by the way, in the main code, we are just outputting sum and n. So what will be the output?
So can you show the function?
Yeah, sorry. Yeah, this is the function.
So the sum variable will contain the sum of all TIDs, and high from threads T0 will only be printed by the first thread launched in the batch.
Okay, any other suggestions, like what will be the output?
Barrier is like notify and yield functions in Java, I think so. It will wait for the other threads will wait for this to be executed for cout.
Yes. Yes.
Sir,
Then cout will be printed. Only then I think there will be some synchronization in the calculation of some value. I think so. It will be now synchronized.
Okay. So what will be the output? Just tell me the output. Yeah, all these things are like
45.
45.
The thread count will be 45. The sum value.
No, I think if you are talking about sum, then we are
25.
only summing TID. So yeah, let us say that we gave 5 as the input, right? Not 10. In case of 10, it should be 45. You are correct. 5, the output will be 10. Because it is summing all the TIDs. So you are saying that output will be 10, right? Assuming that we are launching 5 threads. I mean, running it with 5 threads.
Not sure what it will be the output.
Okay. Anyone else who would like to comment? Okay, if there is no one, then let us try to understand this. So if you see this, right, this hello function will be executed by all the threads in parallel. So what will happen? They will calculate, right, each thread from 0 to 5. Let us say we have 5 threads. Each thread will calculate this thing. They'll do some adding of this TID into the sum, and at the end only one thread. So all of them will come here. What will happen is that at the end only thread 0 will enter this part, right? Now this is the synchronization point. If you remember from the definition, what is this synchronization point? By synchronization point, what I mean is that all the threads should reach at this point, and once all of them reach at this point, only then all I mean they can proceed further. So actually this one, if I speak it more clearly, this one will lead to deadlock. And why deadlock? The reason is that thread 1 to 4, considering 5 threads, thread 1 to 4 will never enter this part, right? And so they'll they'll never execute it, they'll not never execute this part. And thread 0, what it will do is it will wait here for all other threads for all other threads to come at this synchronization point. So there is a deadlock here, and even this thing will not be printed, right? Because the reason is that thread 0 is waiting here for all other threads to come at this synchronization point, and all other threads might have finished this entire hello function and they are waiting here, which is the end of this parallel region, which is the implicit barrier or the synchronization point. So they won't reach even this statement. So what will happen is that T1 to T4 are stuck here and T0 is stuck here. So this is deadlock, right? Deadlock happens when we have multiple threads and each thread is waiting for some event which can only be executed by some another thread in the system. So ideally we are in this deadlock scenario in this case. So if you want to see the execution of this program, I'll try executing this one also. I'll share the console. So economics CPP. So it compiled correctly. Let us run it with 5 threads as we were discussing. And you can see, right, it is stuck. It is neither printing sum or it is neither doing anything. It is just stuck. So this is what is the scenario. We are in the deadlock scenario. Threads are waiting for each other to complete some operation, and we are in deadlock scenario. So this will happen. So the point to learn from this example is that all the threads, when you place the synchronization point like hash pragma OMP barrier explicitly, all the threads within the parallel region should reach this synchronization point, or none of them should reach. If this is ensured, then so let us say that I have 5 threads, right? If none of them reaches, so let us say that I place TIDS 6 and try rerunning this, right? Okay, and let me share this one. So now I've placed TIDS 6, right? TIDS 6, and then there is this hash pragma on the barrier, and I'll run this again with 5 threads. Now we should see some output, because in this case none of them will touch the barrier. None of them are touching the barrier. So either all of them should reach this barrier, or none of them should reach. So this is the point that I was trying to conclude. Let me move back to the slides now. So yeah, it should be encountered.
Sorry for the interruption. Can you just tell me again how this barrier deadlock has been removed? I'm not getting it.
Yeah. Sorry, I'll repeat that. So what I did was I placed TIDS 6. So when I run it with 5 threads, TID will go from 0 to 4, right? So none of them will have TID of 6, and hence none of them will reach this point. So either none of them should reach, or all of them should reach. That is the point. If there is some thread that are reaching and some thread that are not reaching the barrier, then it will cause a problem that will lead to death. So that was the point. Okay.
Sir?
Yeah. So moving. Yeah. Please go ahead.
Just a confirmation. So does it mean that any directive that we are giving will only come into effect if during runtime it is encountered? Like, because since we already have given a directive during compile time only, it should know that thread should have this. Though it has not reached during runtime, but still there is a directive regarding this this particular command. For example, let's say if while like during compile time only, the all the directive must be like compiled, but during runtime we have not reached that part. That is why we are saying that it has not reached deadlock for any, because none of the threads reach. So it means only runtime it affects during
Yes,
runtime.
obviously it will affect at runtime only. So compilation, it is being compiled correctly because there are no syntactic issues, right? But yeah, it is giving runtime error. I mean runtime deadlock at runtime because because of the allocation or the way we are executing it, right? So yeah, in that way you are correct. It depends on runtime. Okay, I think there are no further questions. Then let us move to the another example, not for this barrier, but to the code screen. I think this one. Okay. Yeah, so let us look into this code now. So this is again a very simple code in which we are first importing the libraries, and then we have this int j, int n, and int array, integer array of 10 elements that we are defining, and j is initialized as 1, which is integer. Then we are initializing 0 to n, which is a of 0 is 0, a of 1 is 1, and so on till a of 9 is 9. And then we are doing this thing, right? We are doing this simple thing that is based on the value of I. If I is odd, then we are initializing, if I is even, then we are initializing j as 1, else we are initializing j as 0. And then we are doing a of I as a of I plus j, and then we are printing the output. So quickly, what will be the output in the serial case? It should be quite easy. What's the output in the case of serial program? We are not parallelizing it first. What's the output in serial case?
It will be odd and even number. That is 0 and 1.
Yes. So yeah, that is correct. So in case of this serial program, let me quickly run it also. So the output will be 0 1 0 1 0 1. So that is the out, actually 1 0 1 0 1 0, not 0 1. But yeah, let us quickly run this. This one is scoping class. 1 0 1 0 1 0, as you can see. That is the output. Now, okay, let me share this thing back. Yeah. Now let us say that, okay, I hope you're able to see the code screen. So now let us say that I add this hash OpenMP parallel for now threads 10, that is 10 threads executing this loop of 10 iterations in parallel. Now what will be the output? Will it be same or it will change? Anyone who would like to comment on this?
So it should be same because there's no loop dependency, loop carry dependency.
Are you sure?
Order
Okay,
can
let
be different.
me, sorry. Can you repeat? Sorry, I missed it.
No, nothing, sir. I got confused.
Sir,
Okay.
J variable is facing a data race in this case.
Yeah, so if we go back to our loop carry dependency slide, I think this should be clear now. So I'm expecting everyone to be clear with this point now. So if you see, right, you're able to see the loop carry dependency slide, right? So here, what definition says the same element of an array, or it can, I mean, it can be anything else also, right? Same element of array or same variable. It's just not restricted to the element of the array, but same variable. If it is being written in one iteration or being read in another iteration, that is one case. Second case is it is being written on two different loop iterations. So if you observe properly here, what is happening? Now tell me, is there a loop carry dependency here? And if it is, or I mean, first of all, is it loop carry dependency or not? And if it is, then which case it is? Okay, okay, I'll add this quickly. So there is a loop carry dependency because the same variable j is being read in one, I mean, is being written in two different iterations. So if you see this carefully, let us say that there are 10 threads, right? And there are also 10 iterations. So one thread for each iteration, let us assume that. And this variable j is being written in one iteration, and I mean, written in, let's say, iteration 0, and it is also being written in iteration 1 by different threads. So thread 0 will make it 1, and at the same time it might happen that thread 1 will make it 0. So in some sense there is a data race, but yeah, based on our definition we can say that it's a loop carry dependency also, because writing is happening at the same time in two different iterations. So in some sense there is loop carry dependency. So yes, there is a either data race or loop carry dependency, whatever you would like to say here. Again, let us try running it multiple times to see if we can see different output, right? Apart from 1 0 1 0 1 0 and so on, right? So let us run it for 100 times. Let me share the console. Right. So again, so scoping class dot slash dot out. So if you see here, right, the first, second, third. So every even element should be 1 and every odd element should be 0. But you can see here, right, this 0th, first, second, third, fourth, fifth, sixth, seventh element is instead of 0 it is 1, right? Seventh element should be 0. See, it is 0 for all other case, but it is 1 here. So you can clearly see that there is a look array dependency or a data receiver. So I hope you are convinced with this thing that I'm trying to say. Now, let us see how we can remove this thing, right? So one way in which we can remove is that we can. Okay, so I'll ask you this question, right? Why is this happening? Why this different outputs we are getting? What's the reason for it?
So the J variable is being shared across all threads.
Yeah, so that is correct, right? The J variable is being shared, right? And that is creating this biggest problem that two threads might end up updating it at the same time. So what we can do is that we can make J private, and there are clause using which we can do that, and we'll learn it now. So what we can do is we can specify the scope of the variable explicitly using some clause that we are going to see. So first is the default clause. So by saying this default null, what we are trying to say is that the OpenMP part of compiler is that by default, whatever variables that are unscoped, by unscoped I mean that which are not there in the parallel region, which are not defined in the parallel region. So these are the unscoped variable, right? J, N, and A. So whatever unscoped variable are there, please don't define its scope by your own. Please let programmer define its scope. So that is what is being ensured by using default null. And then what we'll do is that we'll make JS private. So this is the private clause. So this says that this instructs OpenMP that please make this J as private variable for all the threads that are there in the parallel region. And then we can use this clause shared A and N. So we are saying that keep A and N shared, make JS private, and then try running this. Then run this parallel region or parallel for whatever comes next. So I hope you understood this. Default clause defines the scope for the, tries to define the scope for the unscoped variable, which are this one. Private and shared defines the whether a particular variable we want to keep it as private or shared, which is not defined in this parallel region, which is this one, right? For these variables. So yeah, so I hope you got this point. So let us try running this again and see whether we have removed that data race and with correct dependencies or not. So let me share that console back. Right. So again, let me recompile, rerun. So this time, if you see, so this is the latest run. You won't be able to see any other output other than 0, 1, 0, 1, 0, 1, 0, 1, 0, 1 for all the cases. For how many times, whatever times you run, you'll see 0, 1, 0, 1 only. Right. So in some sense, we have removed this data race by doing privatization of that particular variable. So, okay, any questions up till now?
So is the default statement always necessary, or can we like remove that if we only need to specify the scope of single variable?
Yes. Good question. So let us remove the default. And let us also remove this thing, right? Let us say that we just want to, in our scenario, we are just concerned with J, right? That J is making some issues with our code. So we are just okay by specifying private J. So this is also a valid syntax and this won't lead to any issues. So by default, you can eliminate default and specify the private variables like this. So by default, all these are shared, right? Because if you don't specify anything, whatever is defined outside will be taken as shared. So that's the implicit behavior. And by making private here, you are telling the OpenMP that please keep J as private. So if I try running this one, then also it will give correct output. It will compile correctly and will run also. So this, right. So it is giving the correct output. I hope this is clear. If there are no questions, then let us look into one more program. So this is a slightly easier version of this one. So what will be the output of this program? Again, I'm using J and array of n of size 10, initializing it to values from 0 to 9 for each element of A of I. And then later what I'm doing is I'm using this for loop, which is again parallelized by hash pragma MP4 and using 10 threads, specifying J as again private. What will the output? What is the output of this program?
So it should print 1 10 times.
Okay. Any other suggestions? Okay, if there are no suggestions, then let us try running this one to see what will be the output. All right, let us run this. So this one is scoping 2.cpp and dot slash dot out. It is giving all zeros. Now you'll ask why is this the case? So the answer to this is very simple. So whatever you define here, right? J equals to 1, and then you make J as private. So each thread will get the private copy of J. But yeah, that is correct. They have a private copy of J now, but that doesn't mean that they'll also initialize J to 1, which was there in the public scope. So that is the issue. Initialization will not happen. So that is the issue with the private class, and you need to explicitly initialize the J. So that is the observation here. When you use this private clause, make sure that you are initializing the variable that you have defined as private inside your parallel for construct. We can eliminate, we can eliminate this initialization part by using a different clause. We'll see in the next session, but yeah, this is an important point that you should remember. Initialization is needed inside the parallel region. Okay, assuming that there are no questions, let us go back to the slides. So quickly covering these things, private clause, what it specifies that each thread should have its own instance of that variable or the set of variables. So in general, the syntax is this: private followed by followed by the set of variables in the parentheses. So you can specify multiple variables, not just one. So there would have been other variables like k or something like that. You can specify, and yeah, so those variables will be private for each thread in the upcoming parallel region or parallel for. And the applicable directives are parallel for, parallel single. We'll see what is single, don't worry. And yeah, initial value for each each private copy needs to be specified. We saw this, right? If you don't specify the initial value, it will take some random value or zero value, which was in our case, right? That was some random value, and not the one that is specified in the shared scope or the serial region that we saw, right? So this is about the private clause. Now coming to the shared clause, again it specifies that one or more variables should be shared among all the threads. In our case, it was A and N, which we wanted them to be the shared ones. And yeah, syntax is very similar, which is shared followed by the set of variables in the parentheses. And yeah, you can specify multiple variables again. And yeah, coming to the applicable directives, you can apply it for parallel. There are few more directives also, but I have covered the ones that we have seen so far here. So yeah, and last one is the default clause that we saw, which is which specifies the behavior of the unscoped variables in the parallel region. So in our case, unscoped variables were J, N, and A of N. So there are two values that this default can take, right? Shared and none. We saw the none, right? By specifying it as none, we say that those variables used in the those unscoped variable, if they are not, if we are not specifying, if the programmer is not specifying its scope explicitly, then it should give the compilation error. So what it is saying is that if I go back to the code, let us say that if you do this, right, let us say that you just do this default none and you just don't specify anything, you don't specify any scope explicitly, then what it will do is that it will give error. So if I try compiling this one now, no, not this one, this one, it is giving the errors, right? That and not specified in the enclosing parallel, j not specified in the enclosing parallel, a not specified. So basically for unscoped variables, it is throwing error that please specify the scope explicitly. So that is default term, and you can do this also, right? Okay, let me go back. Right, you can do this also, default shared, and then you can specify that private j. So if you do this, then you don't need to write shared and then you don't need to write this thing, because by doing default shared, everything is considered shared. So j and a of n are considered shared, and then you are explicitly specifying that make j as private. So you can eliminate writing this thing, shared a and n. This thing you can remove. So yeah, this thing is equivalent to our previous thing that we did, right? So I hope you got the point that there are two things that we can specify. One is default shared and default none. Yeah, and default shared will treat all the unscoped variables as the share for the parallel region. Okay, any questions up till now for default clause or shared or private, anything that was unclear? Okay, let me quickly check if there is anything in chat that I missed. Okay, I think there are no questions. Then let us move ahead. Okay, now let us look into this directive, single directive. So what single directive says is that if you specify anything followed by, the single directive will be followed by the structured block of code. And what this says that whatever is the structured block of code, it should be executed by only one thread. It can be any thread, like master master thread or any other thread in the team, but it ensures that whatever structured block follows this single directive, it should be executed just by one thread. So if you see the syntax, it is highly simple. Hash #OMP single followed by clauses that you wanted to add here. So, and whatever structured block of code which follows this, it will be executed by only one thread, either master or some other thread in the team. We don't know. It depends on the order of the execution, but it will be executed by just one thread. And the interesting point to note is that again, there is this implicit barrier at the end of the structured block of code, which is here, all the threads will wait. So only one thread will enter, but all other threads will wait at the end. So that is what is the single. And the next one is the master directive. So again, it is very similar to the single directive, but the only difference is that the structured block of code will be executed by one thread, which will be the master thread. In the case of single, it will be any thread which can be master thread or non-master thread, but here it will be definitely the master thread. So the syntax is again highly simple, hash #OMP master followed by clause and then the structured block of code. And this structured block of code here will be executed by just the master thread, for sure. And unlike single directive, it does not have the implicit barrier at the end of the structured block of code here. So master thread will execute this structured block of code, and all other threads will continue. They won't wait at the end of the structured block of code. So I hope this is clear. Any questions related to this single or master directive? Okay, if there are no questions, then let us look into a code, sample code for this. If I have sample code, yeah, I think it's this one. So again, our initial hello world program, which is the best for illustration purposes. So again, we are calling this hello function inside this parallel region with thread count number of threads, and inside that we are doing the rest of the computation in a similar way. And then I've placed these two things, right? Hash pragma-mp master and hash pragma-mp single. Let me remove this nowhere for now. But yeah, what will the output of this program? Can anyone tell what is the output? I hope that question was clear. Like we have kept the entire programs similar, and we have also commented the sum for now because we just don't want to print the sum or anything like that. The only printing that is happening is inside the single and master part, and we are interested in figuring out what will be the output. Anyone?
So only the TIDs of master thread and the thread that executing a single block should be printed.
Master thread, and sorry, I missed the second part. What's the second part?
The master thread and the thread executing the single block.
Yeah, so specifically speaking, it should print 0 followed by any TID from 0 to 4, right? So something like that, this it should print 0 and then space and then anything from 0 to 4, right? Because those are the TIDs of the threads. If we are launching with 5 threads, I'm assuming that we are keeping threads as 5. So any questions? So let us try to execute also, but any questions, then I can pick up. Okay, let me share my screen. I haven't saved the program. Let me save the program. And let us run this one. Single. Yeah, so it is saying please specify the second argument, which is number of threads, and we specify 5 threads, right? So now the output is slightly jumbled because the standard output, all the threads are racing for the standard output. So output should be jumbled, but you can see that for a few of the cases it is giving the smooth output. And you see that the first output that it prints is always 0, which is aligned with our thinking, right? That first output, the first TID that it should print should be from the master thread, which is the thread with TID 0. So thread with TID 0 is our master thread, and always it will print 0 followed by any TID other than, not other than, but any TID from 0 to 4. So that is what is happening here, right? So I hope that this point is clear. What is single, what is master? If there are any questions, then please feel free to ask. Otherwise, we'll move ahead. Let me share my slides. Okay, we're done with the master single. Now let us come to no wait clause. So no wait clause essentially allows us to override or remove the implicit barrier that is there in each of this, each of the directive where we have implicit barrier, right? So we have this implicit barrier for many cases, right? For parallel and single and so on. So the syntax is highly simple. Hash pragma-mp directive followed by no wait clause. So let us go back to our example for this single section. So if you see here, you can specify no wait here. And what it will ensure is that all threads will not wait here. So by default, if I don't have this no wait, then what will happen is that each thread will reach till this point. Then only one thread will execute this, but all the threads will wait here at the end of structured block, right? But by writing no wait here, what will happen is that all other threads, apart from the one who is executing this single section, will not wait. They'll go ahead. They'll proceed with some calculation that they want to do. So the classic example that I would like to give here is that for the for clause, like let us go back to our whiteboard. So if you see this, right, you can have something like this. So you can have, I hope you're able to see my whiteboard now. Hash pragma OMP parallel, and you are running this structured block of code in parallel, right? Now within this you can have hash pragma OMP for followed by for loop, followed by for loop here. So what will happen in this case is that this is the parallel region now, right? So there will be multiple threads running this parallel region, right? So and what will happen is that when it encounters this, each thread encounters this part, it will whatever the loop that follows it, it will divide the iteration. So this hash pragma for is work sharing construct, right? So here all the threads, let's say there were 4 threads, then 4 threads will divide this loop of, let's say, 12 iterations equally. And what will happen is that each of these threads will wait at the end of this hash pragma MP4, at the end of this hash pragma MP4. So there is this implicit variant at the end of hash pragma MP4, and this can lead to a problem, right? Let's say what you want is that let's say thread 1, if it is done with executing this loop, then you want that thread 1 to continue its execution ahead. You don't want it to wait for other threads to finish its for loop computation. So in that case, what you can do easily here is that you can specify no wait. This will ensure that the threads who are finished are done with its loop computation can progress ahead, and it will not wait for other threads to finish its for computation. So this can improve efficiency in some cases, but yeah, you need to make sure that the code that you have after this for should not be dependent on this code, the computation that you are doing for. So that is one restriction that you should remember. So I hope you understood this no wait clause. Basically, it removes the, or I mean, it basically, yeah, it basically overrides the barrier that implicit barrier that we have in the directive. So that is about no wait, and I think I have a couple of more directives that I wanted to share. Yeah, I think the next one is if clause. So this one is generally helpful. So its syntax is simple: if followed by a scalar expression, and again you can apply it for parallel, and so on. The directives that we have seen so far. And what it does is that if the scalar expression returns true, I mean, if this turns out to be true, then it will execute that structured block of code that follows that parallel or parallel for in parallel. Otherwise, it will execute in serial. So yeah, let us look into the example for this again. So let me go back to our code screen. Yeah, so I hope you're able to see the code screen. And yeah, so this one, yeah, let us look at this example itself, right? So we had this loop, right? And let us say that you want to run this loop in parallel. I mean, you want to divide this loop in iterations of this loop among threads only if there are sizable number of iterations, right? Otherwise, you would like to run it in serial because the serial performance might be better than the parallel in that case. Because if there are less iterations, then yeah, you can run it in serial and it might be even quicker sometimes. So in that case, you can write this if clause specifying that if n is greater than 100, then only run this this piece of for loop, this for loop in parallel. That is, you apply the work sharing construct only if n is greater than 100. Else, you will run this in serial. So the master thread will run this entire loop in serial, one after the other. And if there are more than 100 iterations, 100 or more iterations, then each thread will, the work will be shared among, the iterations will be shared among the threads. So I hope this is clear. Any questions on this class? So we are just looking at some clause that I would like to highlight so that we can use them in later lectures. So I think this was the last one. I think, yeah, this is the last one that I wanted to share. If there are any questions, then please let me know. Otherwise, I think this is what I wanted to cover for the today's session. Are there any questions?
I have a request.
Yes, please go ahead.
Is there any chance for us to see any real-time project in maybe towards the end of the training program? How all the concepts that we see here are coming into the action, maybe some scientific project or something like that. So that will improve our knowledge.
Yeah, so we'll cover few applications, but covering a real world project in a lecture, 1.5 hour lecture or 1 hour lecture or a session like this is highly difficult because there are many moving parts and so on. So I can point out few of the pointers here, but yeah, we won't be covering any specific projects, real world projects for this one, these sessions.
Okay, maybe you can tell us theoretically also how this is being used. Not by seeing the code, maybe some case studies or something like that.
Yeah, so in that way, we'll be covering some applications, but if you have any specific project in mind, then do let me know. Like, there are a few applications that will be covered. But
Okay.
yeah, very complicated projects we won't be covering because, again, understanding that theory will again take some more time. And since we have already decided what we are going to cover, and let us say if you want to put some
There'll be some
complex
applications, right?
yeah, there are some applications, but
Okay.
if you are talking about some let's say some paper that are published which are based on this OpenMP or something like that, and if you want me to cover that during any one of the sessions, then it will be difficult for me because the time will be restricted, right? Will be restricted with time because we
I
want
understand.
to cover
Maybe
the
you can
content.
share the link of your paper so that we can go through in a self study or something.
Yeah, sure. I can share some papers, research papers where you can see some applications or how we can, see like in real world where this is being applied or this being used in research or something like that.
Okay, maybe you can share the links in the our Google group.
Yeah, I'll share. Yeah.
Thank you. Thank you. Thank you.
So I have one thing I want to share with you. So I tried to
Yeah.
implement that integration functions that you showed us during the previous classes, and I
Yes.
went a step ahead and I tried to time that in comparison to the serial versions of the same functions.
Hmm.
So I like tried using reductions and everything, like other atomics to maintain the integrity of the result. But for some reason, the serial function was performing much better than the parallel function. So what can be the problem? Is that due to the semaphore locks that are being applied, or there might be something else at play?
So I think, okay, I haven't, frankly speaking, I haven't tried timing the serial and parallel versions, but sorry, I think the reason can be two parts. One is that we might not be using parallelism up to that extent. So maybe you can try running it with more trapeziums, more threads, and see like how many threads, for how many threads it is giving the, I mean, what is the time that is being measured for different number of threads, different number of trapeziums. That is one part. And let us say that even after increasing threads up to some extent, it is not giving that particular, I mean, performing better than the serial part, then I think the reason can mostly be the synchronization thing that we are implementing. But I think you should get some performance benefit, provided that the computation that you are doing, right? The computation that you are doing is very expensive. So in our case, I think it is expensive computation because we are doing quite a bit of work on that. But yeah, I think you should increase the bounds, try increasing the bound instead of 1 to pi, increase it, like make it a bigger thing so that for loop inside it is executing for very high number of iterations. Try increasing the bound, increasing the number of trapeziums, increasing the number of threads and so on, and try running it. I think you should see some benefit out of
So the number of
running it.
you can modify the number of trapeziums based on a parameter, and I tried executing that to 10,000 as well, but there was always a difference of almost like 2 order magnitudes. So it was the parallel code was executing like 100 times slower almost than the serial code for some reason. I'll share you the code if it's possible for you to look at that and maybe give me some inputs.
Yeah. Can you share the code in the Google group
Yes,
after
sir.
this
Yes, sir.
session so that we can,
I'll share the
all of us
file
can
in
take
the.
a look?
Yeah, sure, sir. Thank you, sir.
Okay, any other questions? I'll be there here for a few more minutes. Yeah, and if there are no questions, then yeah, we can call it a day. But yeah, I'll wait here for a few more minutes. I think 2, 3 more minutes, and then yeah. Okay, if there are no further questions, then let us call it a day and see you all on next Saturday at 5 p.m. Thanks for attending. Bye.